Hochschild homology and topological cyclic homology from Kathryn.
Thank you very much. I'd like to thank the organizers for giving me the opportunity to come back to MSRI and to talk to you about subjects that I find very interesting. The work that I'm going to be talking about today is actually entirely the work of other people. So it's a challenge. A number of them are actually in the room, which makes this even more challenging. So I hope they won't hesitate to intervene if I start saying things that are too false. So this is supposed to be a series of 3 lectures leading up from sort of classical description of Hochschild and cyclic homology to very modern treatment of topological Hochschild and topological cyclic homology based primarily on the recent work of Thomas Nikolaus and Bökstedt-Hsiang-Madsen. But it's a long path to get there. And if I dove in directly to talking about the Nikolaus-Scholze work, I think it would be unfair to almost everybody in the room. So today what I'm going to do is motivate the purpose of these lectures and to give an overview of what's going to come in the next 2 lectures so that the algebraic geometers can decide whether or not it's worth coming back for the other 2 lectures. But it's a very deep, very fascinating subject, and I hope you'll agree with me at the end that it's very beautiful. I appreciate the fact the organizers obliged me to really learn this material well enough to try to explain it to you. So one thing you're going to notice is that the timing of these lectures is well chosen in that I'm going to use simplicial methods, which Ben introduced in his talks and used in some detail and have come up in a number of other talks. In particular in the 3rd lecture, we're talking more about infinity categorical methods, so there it's very good that we had the lecture series on those. And also, I'd like to make a reference to Sam Raskin's first talk when he said that, the way we do mathematics is there are certain things that we want, and then we compute some stuff and realize that, no. And then you realize what you actually can do. And so it's going to be the same kind of process going on here. So first part of the lecture, motivation and overview. Okay, so in the spirit of Sam's talk, what do we want? We want to compute the algebraic K-theory of a ring, either a traditional commutative ring or a simplicial ring or a ring spectrum or something like this. Why do we want to compute K of R? Because the algebraic K-theory of rings contains lots of important number theoretic information. And also, if your ring has some sort of geometric meaning, so for example, it's the group ring of the fundamental group of a space, then it contains a lot of important geometric information as well. So this is a really important invariant that captures a lot of things that we would like, encodes a lot of information that we want to understand. But there's a big problem. It's really hard to compute algebraic K-theory. And so we really have to figure out some tools that are going to help us to do these computations. Okay, so what are we going to do? So the method of attack that I'm going to describe is as follows. What we're going to do is construct and hopefully compute various approximations to algebraic K-theory. So construct and hopefully, don't know why it's banging, compute various approximations to algebraic K-theory. I'm going to describe certain of them and determine also how good these approximations are. So that's the way we're going to try to go about this. Okay. And so before I dive into really some of the overview of what's going to happen in the next lectures, I'm going to introduce a bit of global notation. There's a certain player that comes into this game a lot, which is the following. Somebody we're going to see a lot in this talk is somebody I'm going to denote T for the circle group. So the circle, the usual circle, but really seen as a group. And we'll see very quickly why the circle comes into play when we go about studying these approximations to algebraic K-theory. So let me start by talking about, or giving a brief overview, because we're going to revisit this maybe towards the end of this lecture, most likely during the lecture tomorrow, some classical approximations. Okay, so for the moment, I'm going to let A be a flat Z algebra, maybe simplicial, maybe differential graded, maybe just an ordinary ring. So perhaps simplicial or DG. There are ways of dealing with both here. And what I'm going to talk about is a first approximation to the K-theory of this ring A, which is its Hochschild homology. So the Hochschild homology we're going to get from looking at a certain simplicial construction built from the multiplicative structure and the unit of this ring A. All right. So I'm going to build a simplicial abelian group. I'll denote like this. Simplicial object in abelian groups, or it could be simplicial object in differential graded complexes over Z or whatever. But let's just keep it a little more simple here. So what's it going to look like? So the nth term in the simplicial abelian group is going to be A tensored n plus 1 times. And when you're describing a simplicial object, you need to give the face maps from the nth term to the n minus first, and the degeneracy is going back up. So you're going to have face maps like this. They're going to do what? I'm going to use the multiplicative structure here to give these face maps, so to decrease the number of factors. So if I have an A0 tensor AN, there are kind of two possibilities. So for I between 0 and n minus 1, what I do is the following. I'm going to multiply AI and AI plus 1 in the algebra A. And for the nth term, I'm going to do something a little bit tricky. I'm going to bring that nth factor around and multiply on the left. So it looks like this. AN A0, AN minus 1 for I equal to n. So what we see is that we actually have an action of the cyclic group on each term here. So here, for example, this is not what I wanted to say. Yes? Yes. And so, yeah? Yes. When in the commutative case, yes. So the question is whether you can see this as sort of a simplicial ring generated by the circle. So there is a way in which you can describe this as A tensored up with a circle, simplicial circle, at least in the case when A is commutative. So this is where the circle is coming from. So we really have this cyclic action here. And because of this cyclic action, what we have is not just a simplicial abelian group, it's actually a cyclic abelian group, so that when we take its realization, meaning either in some sense giving us some sort of topological space or giving us a chain complex, depending on where you're realizing, you're actually going to get an action of S1 on this complex. So this gives us I should be consistent with my own notation, an action of the circle group on some sort of geometric realization of this, where you can take the geometric realization, use some kind of space, or if you prefer to think about chain complexes, you're just taking the usual way of associating a chain complex to a simplicial abelian group, and you're getting a T action. So what do I really mean by this? So there's a way of making this explicit on the chain level, but this leads to other sorts of invariants, one of which is cyclic homology of your ring. So let me just write this as HHA without the dot, that you get by taking the homotopy fixed points of this action. So either in chain complexes, you have some sort of notion of homotopy. You can make homotopy orbits of your T action, or you're in spaces and you have homotopy orbits. And you also have what's called negative cyclic homology, which comes from looking at the homotopy fixed points of this action. So if you're thinking about this in terms of chain complexes, tomorrow or maybe later today, I will give you actually a chain model for what's going on when we're looking at these homotopy orbits. So an explicit and nice chain model, which was first really noticed by Kohn. And so, or if you prefer, you can think about these as constructions in the derived category of Z or something like this. So anyway, we have these constructions, we have these various invariants. And as I said, one of the things we want to do is to see how good our approximation is. So there's a theorem due to Goodwillie from 1986, where he showed the following, that there is a natural map and he was looking on the level of the homology groups of these complexes, or the homotopy groups if you're looking at the geometric realization really in spaces or simplicial sets. Let's call it the trace from, so these are now the K groups. Oh, sorry. Yeah, I'll call it A. To the groups that you get, the homology groups that you get from this complex. So it's natural in this case for all simplicial rings. Such that we have the following picture. There's a certain, because this is a natural map, anytime we have, so for every F from A to B, a morphism of simplicial rings, such that it's a surjection on pi 0, with nilpotent kernel, all right. I have to wait for the punchline. Anytime we have a morphism like that of simplicial rings, then there's a diagram the naturality of the trace gives us a commuting diagram relating K-theory of the two rings and their respective negative cyclic homologies that has a really nice property. So if I look at the K-theory of A tensored up with Q, the K-theory of B tensored up with Q, and I look at the negative cyclic homology of A tensor Q, the negative cyclic homology of B tensor Q. So these vertical maps are induced by F. Here we have the traces. This diagram is what's called homotopy Cartesian. So what does homotopy Cartesian mean? It means that, in some sense, the difference between these two here is the same as the difference between these two here. More precisely, we can look at, there's a long exact sequence of K-theory groups, K-theory of A to K-theory of B to K-theory of some sort of kernel, that, so if you have a long exact sequence that involves this and some third thing, and we actually have an isomorphism on those third things, which we write like this. So, i.e., the relative K-theory of the map itself is isomorphic to the negative cyclic homology. So just these guys just fit into long exact sequences with this and this. It's sort of like what the error is, what the difference is between these two is the same as the difference between these two. So it's a relatively good approximation to algebraic K-theory in that sense. Yeah? Well, we can talk about that afterwards. I'm not going to go into that kind of detail. Otherwise, okay. So this composite here is sort of so what I'm going to say is that this comparison map that we have between K-theory and negative cyclic homology is obviously really important because it's giving us this idea of how good an approximation we're getting. And so we're quite interested in studying it. So you have this, and because this guy is the homotopy fixed points of the circle action on Hochschild homology, we actually have a map down to Hochschild homology as well. So this was this trace here, which is sometimes called the Jones-Goodwillie trace. And this composite from here to here is what's known as the Dennis trace. And the idea is to use these sort of trace maps from K-theory to various approximations to K-theory to be able to learn things about K-theory. So these are called trace theoretic methods, which have turned out to be extremely successful in giving us information about K-theory. Dennis trace is also constructed in other ways. It just turns out that it factors through this particular Jones-Goodwillie trace. Now, when I was discussing these things with Lars yesterday, he pointed out that if we think, a good way to think about K, the K-theory is some sort of higher version of the determinant. I mean, the determinant is really what K-theory is all about. So the K-theory, algebraic K-theory is some sort of higher version of the determinant. And what we're doing with these traces is sort of trying to understand determinants in terms of traces. Okay, but the question now so can we generalize Goodwillie's result beyond the rationals? Right? We like to go beyond the rationals. We'd like to be able to work integrally or something like this, be able to say something. And the answer is yes, we can to a certain extent. And so the answer is going to be via what Waldhausen called brave new algebra. Brave new algebra techniques. So the idea is that we're going, instead of working with rings or simplicial rings, we're going to work with ring spectra. So I'm going to go into more detail in the lecture tomorrow about spectra and so on. But I'll say a few words today. And the idea with brave new algebra is that instead of doing ordinary algebra over the integers, we're going to do this brave new algebra of ring spectra, replacing the integers as the unit by the sphere spectrum. So I'm going to say a few words about these brave new algebra methods. And this is really, the point now is really just to give, as I said, an overview, and then we'll see a lot of these things in more detail later in the lectures. So, second point is brave new algebra approximations. Okay. So what's the idea here? So now our A is going to be an associative ring spectrum. So as for a spectrum for the moment, we can just think of it as a sequence of spaces. And where there is a map from the suspension of the nth space to the n plus first. And then there are various, on the category of such objects, there is a monoidal structure so that one can talk about a homotopy meaningful monoidal structure, so that one can talk about actually having ring objects in this category of spectra. And that's what we mean by ring spectra. So let A be an associative ring spectrum. Later I'm going to specialize to a very particular kind of spectra, which are called orthogonal spectra, but that's too much detail for now. So the idea is as follows. So we're going to make an analogous construction to what's still here on the board. We're going to get some sort of simplicial spectrum as follows. So we'll have a simplicial object in spectra that is going to look like this. And so on. So this would be our 0th, 1st, and 2nd terms, and so on. Here, what's written as SMASH, that's the standard notation in stable homotopy theory for what you might think of as tensoring over the sphere spectrum. So the sphere spectrum is just a sequence of spheres S0, S1, S2, S3, and so on. There's obvious map from the suspension of the nth term to the n plus first. So that's the way you can think of this as kind of generalization of what is up there. The face maps are identical. It's also given by multiplication and using this twist map so that we have cyclic actions again, and so on. And because of these cyclic actions, once we realize this, we take the geometric realization now and get some kind of spectrum again, this spectrum will admit an action by the circle. So the cyclic structure gives an action of the circle group on this geometric realization, which is now a spectrum. Now, there are a few kind of technical comments one needs to make, that this thing is not going to be nicely homotopy invariant if we're not careful about either restricting to ring spectra that are cofibrant in some sense. So if you want to think as an algebraic, it's sort of projective or flat in some sense. But just a few remarks about this. To get something that's a homotopy invariant, you have to use a construction that's a bit more subtle that I'll probably remind you of tomorrow, or tell you about tomorrow. We're going to replace this iterated smash by something that's equivalent to it by an equivalent construction due to Bökstedt that I will recall in more detail later. And if we use Bökstedt's model for THH, so replacing this ordinary smash project by something that's a little more complicated to describe but is equivalent, then it turns out that if we take THH, now it has a circle action, as I said, because of this cyclic structure on the simplicial object. And if we actually take the fixed points of this with respect to a finite subgroup of the circle group, it's still going to be something that's homotopy invariant. So we can replace A by something that's equivalent to it without changing the homotopy type of this thing. So this thing is what we call homotopically meaningful. You can change your ring up to homotopy and get the same answer. So what kind of structure do we really have on this thing? It's not just a circle action. It's something more subtle. So the circle action is actually, when we look at the restriction of the circle action to actions by the cyclic subgroups, there's interesting Frobenius type structure that shows up that I'm not going to describe in detail. I'm just going to give a hint of. We'll get into more detail later. So it turns out that this object here is a T spectrum. So it's a spectrum with a cyclic group action. Together with, for lack of a better term, I'll call for the moment some sort of Frobenius map, some kind of Frobenius structure. A bunch of maps that all play together in a compatible way, that involve these fixed points of the cyclic groups on THH. And these two things together give us what's called a cyclotomic structure. So the THH of A is what we call a cyclotomic spectrum. And using this cyclotomic structure, we can do more. So you use the cyclotomic structure when you construct the brave new version of cyclic homology. So I'm saying that in a very rough way because it turns out that one needs to use more than just, it's not going to be just taking either the homotopy fixed points or the homotopy orbits of the T action. You really need to use the cyclotomic structure in a deep way. Okay. So let me explain what we're going to do. So we want to somehow relate all of the spectra of actual genuine fixed points of the cyclic groups on these spectra on THH. So So a brave new cyclic homology so this is Bökstedt-Hsiang-Madsen from 1993. Very beautiful and deep paper from then. So if we look at inclusion of fixed points, this just gives us a map from THH of A, its CPN fixed points, to THH of A, CPN minus 1 fixed points. And this is usually called F because it really is a kind of Frobenius. It turns out that if you look at pi 0 of this gadget, that it's actually the p-typical width vectors. And so this really does look like a Frobenius. So for those who know about bit vectors, that's what justifies calling this an F, because it really is a Frobenius. And then the cyclic atomic structure, in a way that I'm not going to describe today, but promise that I will describe in gory detail over the next 2 days, gives us another map, which is called R, which goes between the same fixed point spectra R, because if you look at what's going on pi 0, then it really is a restriction map on the corresponding bit vectors. So you have these two maps. This one easy to find, this one a little more complicated, as we'll see. And so what can we do with this? We're going to use this extra structure now to define some sort of cyclic type invariant, which is built from THH, but is a better approximation to K-theory than THH itself. There are many times when THH, which is relatively computable, is unfortunately 0 when you know the K-theory shouldn't be such. So it's not the best invariant. So now we're going to set. We're going to start building some other invariant from these Frobenius and restriction maps. So first, we're going to fix a prime P, like this. And we're going to look at what's called TR, which we get by looking at the following pair of maps. So we have our family of all of these guys. And so this is living in some category of spectra, which has a homotopy theory associated to it. It's a model category. So we can talk about homotopy limits and homotopy co-limits in these categories. And so here we'd be taking the homotopy limit over all of the R maps. Okay, so we're sort of restricting all the way along. And then the p-typical version of our cyclic invariant, TCAP, is then, again, a homotopy limit. But, OK, so one thing I should have said, and I didn't say, is that these F and R maps, they commute. So and because they commute, there are induced maps here between the TR constructions, one of which is just going to be the identity, and the other of which is induced by F. So you're trying to look at the difference between the way the identity and the Frobenius act on these TR constructions. And that gives us what you could call p-typical topological cyclic homology. Actually, write it out in all words for once. So you can look one prime at a time in this way. But it's also possible to sort of put all the primes together, and that's what I want to explain now. So we're going to put all the primes together. So what we're going to do is define the topological cyclic homology of A. So it fits into sort of homotopy pullback. So on the one hand, I'll write it like this. So it's the homotopy limit, again, of the following two arrows. So what I'm going to do is have two arrows that map into the product. Sorry, that's not really visible. I'm going to look at P, the set of all primes. Then I'm going to take the product over P in P of, I'm going to take these THA spectra. And there's a way of P completing these things, just as you can think about P completing rings in general. So this notation I'm using here is doing some sort of P completion of these structures, really focusing on the P information. And then we take the homotopy fixed points of this circle action. It's a rather complicated gadget, but it's sort of building in. We're looking at THH, and we're focusing at each prime on the particular information related to that prime. Okay? And then we can map into that in various ways. By looking at the maps into each factor, we have a map from THA itself and its homotopy fixed points, which was kind of our implicit candidate for something like negative cyclic homology, but it's not quite complex enough. And then here we have a map from the product over all primes of the P-typical part here, so completed at P. So we have these two maps into this product here. This just factor by factor, the map from TC to THH. And here, mapping into the multiple factors. And it's when we pull this back that we get, let's see, I have some colors. So TCV fits into this picture like this as a homotopy pullback of this thing. So you're putting together all of this P information. All right. So the reason for tackling this brave new algebra is because we wanted a non-rational version of Goodwilly's result. So Goodwilly's result was saying that we had this really nice comparison between algebraic K-theory of simplicial rings and negative cyclic homology of simplicial rings. So it turns out that Goodwilly's result does generalize, where now we're going to replace negative cyclic homology by this topological cyclic homology. So here's a theorem that is due in various forms to Dundas, Goodwilly, and McCarthy, who proved various versions of it. And then they have a book that came out a few years ago about algebraic K-theory and trace invariants, THH and TC and so on, which is a very nice summary of these things, and in which they proved a more general version that sort of englobes all of their previous work. So you can find this in their book, which was published in 2013. And the theorem says the following. So as they say it themselves, the difference between K and TC is locally constant. And if you look in the introduction to their book, they have a really nice graphical explanation of this, sort of in terms of derivatives of curves and so on. But more precisely, we can say the following, that there exist natural trace maps again from the K-theory of A to the topological cyclic homology of A. And this one is usually denoted TRC for cyclotomic trace. And then obviously map from TC to THH. This composite here is what's called the Dennis trace again. And this TRC is what people call the cyclotomic trace. So we have these natural maps that enable us to talk about comparisons between K-theory and topological cyclic homology. And now we hope for a result like that of Goodwillie about K-theory and negative cyclic homology of simplicial rings. And so we can say such that if I have a morphism of ring spectra, such that, again, it's exactly the same condition. Pi 0 of f is supposed to be surjection with no potent kernel. So again, when I take pi 0 of a map of ring spectra, I end up with a homomorphism of rings in the classical sense. So pi 0 of f is surjection with no potent kernel. For all f like that, if I look at this diagram, K-theory of A to K-theory of B. So I'm talking about K-theory of ring spectra. You're used to thinking about K-theory of rings or K-theory of simplicial rings. The point here is that we can play a very similar game with ring spectra. You can look at the category of modules over a ring spectrum. You look at the compact objects or the perfect objects in that category of modules, and then you can take usual K-theory of this category of modules. So this is a theory that was well developed by Waldhausen. All right, so we have these notions of K-theory for ring spectra, generalizing notion of K-theory for rings. There's the cyclotomic trace relating K-theory of A to TC of A and K-theory of B to TC of B. And this diagram is, again, homotopic Cartesian. So there's an equivalence on either the fibers or cofibers of these maps here. So in that sense, topological cyclic homology is a good approximation to K-theory. And by doing computations for topological cyclic homology, we should be able to learn things be useful for K-theory. And I'll talk a little bit later, or tomorrow most likely, about various properties of THH and TC that are very useful for understanding its structure. But for now, we're going to switch gears and move to the world of infinity categories. So I want to talk about some infinity categorical innovations. So why would one want to move into infinity categories? So I must admit that I am somebody who has spent most of her career thinking about model categories rather than infinity categories. I am a recent partial convert to thinking about partial, to thinking about infinity categories. And there are situations in which there are things that just cannot be expressed, either cannot be expressed cleanly or cannot be expressed at all in the context of model categories. And so it's worth it to work in this world of infinity categories, even though it can be somewhat intimidating. And in particular, as I'll mention in a moment, by exploiting infinity categorical machinery, Nikolaus and Scholze managed to clean up this whole story about cyclotomic spectra and TC in a way to make it much, in some sense, less combinatorially intimidating, and also to lend itself better to computations. But before I mention that, I want to say something about sort of the universal properties of K-theory. So there's a paper by Blumberg, Gepner, and Taboada from 2013, in which I will say this very roughly, because I'm not going to get into the fine details of presentable stable infinity categories, but the idea is that so there are two versions of K-theory. There's a connective version, which is not going to have any homotopy groups in negative dimensions, and there's a non-connective version, which can have homotopy groups out to wazoo. And it turns out that connective algebraic K-theory is the universal additive invariant. So what do I mean by that? So in particular, additive K-theory, it's going to invert Morita equivalences, it's going to preserve filtered colimits, and it's going to send split exact sequences to split cofiber sequences. So there's a sort of very definition of additive, which is kind of a homotopy theoretic generalization of what you think of as additive in the algebraic world. But the point is that this means that anytime you have an additive invariant, you're going to be able to have a map from algebraic K-theory to that particular additive invariant. So let me just write a couple words here. Inverts Morita equivalences. Preserves filtered colimits, so there's already some kind of additivity there. And send split exact sequences to what one might think of as kind of exact sequences in category to cofiber sequences. So basically, if you're used to thinking algebraically, just think of additive in the usual sense. But the point of this is to be able to give us, for universal reasons, maps out of algebraic K-theory. That's why this is important. So it's for the existence of maps out of which is the kind of thing we want when we're looking for trace maps. So one can construct trace maps by hand, but sometimes you can know that they actually exist just because your invariant is of the right type. And then the non-connective version, this is where you can have negative groups in negative dimensions as well, is the universal localizing invariant. So this means that it's additive, plus it has a property that all exact sequences, not just the split exact, are sent to coviper sequences. So it turns out that THH, TC, and other types of invariants like that, like what's called TP, which is the homotopy fixed points there, homotopy fixed point of the circle action, these guys are also so the universal property gives us for free that there is a trace and it's unique up to some contractible set of choices. So that's a really nice paper in which taking an infinity categorical approach really enabled Blumberg, Gepner, and Taboada to say in a very clear way, a very clean way, what had been sort of implicit in people's understanding of K-theory over the years. And I should also mention in passing that Clark Berwick has also worked on universal type understandings of K-theory in the infinity categorical context. And has a very nice approach to that as well. Okay, now comes a moment we've all been waiting for, or at least maybe. Let me start by saying today just a very few words about what Nikolaus and Scholze did. In an article that appeared, it was published just at the end of last year, but it's been on the archive for a little while. What did they do? What's their contribution to this story of approximations of algebraic K-theory? So they provided an elegant infinity category theoretic. Approach to cyclotomic spectra. So they have a very surprisingly simple description of what it means to be a cyclotomic spectrum, as long as you're willing to work in this infinity category context. So they come up with some definition of cyclotomic spectra that looks too easy to be true. Like, could that possibly be all that it is? And they show which they then proved to be equivalent to the usual definition of cyclotomic spectra. And that's really sort of the main theorem of their work, proving, sort of setting up this whole framework and proving that their approach to cyclotomic spectra is equivalent to the classical one. And this leads to a very clean description of TC. So they have a way of constructing THH of A as a cyclotomic spectrum in their sense, in their new sense. And then it turns out that if you use their new definition of cyclotomic spectra, then there's a very sort of straightforward way to think about what topological cyclic homology is. It really is kind of sort of the sphere spectrum fixed points in this category of cyclotomic spectra, a very reasonable kind of definition, and it turns out to be equivalent to usual TC. So I'll just write that here. So I'll put this in quotation marks. A straightforward construction of have THHA as a cyclotomic spectrum in their sense. Now, when I say straightforward, it's also combinatorially challenging, at least in the case when A is an associative ring spectrum and not a commutative one. I will actually be able to explain to you how the cyclotomic structure, where it comes from in the case when A is commutative, but the associative case requires a bit more work. So it will be left to the interested reader. OK. So thinking back to Sam's talk, he said, OK, you have a want, you can't quite realize it, then you adjust your expectations, and then you see what you can actually compute. And it turns out that this Nikolaus-Scholze approach to TC and THH actually makes it easy, well, easy, no, I exaggerate, easier and cleaner to do some computations for THH and TC that were either more difficult or out of reach without this. So for this, I'd like to thank Lars Hesselholt for giving me early access to the chapter of the homotopy theory handbook that he and Thomas Nikolaus have been writing, in which they explain how you can use TC to do interesting computations. So I don't have time to describe very many, but there's something that's called Bökstedt periodicity. So Bökstedt periodicity was unsurprisingly established by Bökstedt originally, though if I've understood correctly, it appears only as a preprint and is never actually published. So Lars and Thomas have actually provided a proof in their work. And so it turns out that there's a spectral sequence, which is called the Bökstedt spectral sequence, that one can use for doing computations of homotopy groups of THH. So it converges from an E2 term, which is the usual Hochschild homology of the graded ring that comes by looking at the homotopy groups. So here we're going to say A is a commutative ring spectrum, or E infinity for those who want to be more precise, converges from the Hochschild homology of the graded ring associated to A that we get by taking its homotopy groups. What does it converge to? It converges to the homotopy groups of THH. So it's a way to compute the homotopy groups of THH from the Hochschild homology groups of the graded ring of homotopy groups. So using the Bökstedt spectral sequence, one can compute that. So this is what we call THH star of A. If I take HFP, which is the Eilenberg-MacLane spectrum associated to FP, so it's the graded ring spectrum that represents FP cohomology theories, that this thing is actually isomorphic to a symmetric algebra, an FP symmetric algebra, on what you have in degree 2. So there's a natural map from THH2 into THH star. This, because H of FP is a commutative ring spectrum, this is also commutative. So there's a map from the symmetric algebra on this guy into here. This turns out to be an isomorphism. There's a map going this way. And the dimension over FP is just 1. So it's a symmetric algebra, a polynomial algebra on one generator. Now, I don't have time to talk about it, but Bat, Morrow, and Scholze have generalized this Bökstedt periodicity to perfectoid rings as well. And then you can draw conclusions from this particular isomorphism for topological cyclic homology as well. And you can even, by going through this process and make its extension to perfectoid rings, you can actually obtain Bott periodicity as a consequence of this kind of. So you can show, starting from this, doing a generalization to perfectoid rings, and then you can go on and prove, using also work of Clausen, Matthew, and Morrow, that so I'll just write this, at least this down. So this leads, so I'll make a long arrow because it's a long multi-step process, but it leads in the very long run to being able to prove that if I look at the topological K-theory of the complex numbers, that it's isomorphic to a polynomial ring over Z of the degree 2 part of this, and the dimension here is obviously 1. So you can get Bott periodicity as a consequence of Bökstedt periodicity if you make all these nice extensions that Bat, Morrow, and Scholze did, also leaning on work of Clausen, Matthew, and Morrow. So tomorrow, we'll think about classical things and brave new algebra. Thank you for your attention. Right, so if you want to think about original rings, then you can use this Eilenberg-MacLane spectrum construction that gives you a way of embedding commutative rings in commutative ring spectra, so that this theory actually extends what you already had for rings. And it will agree. That's the point. Oh, actually, sorry, that's not true. THH contains more information than just HH. So that's one thing that's really, it's also even useful just for ordinary rings to make this extension to the topological invariants. Yeah.
Do you have an idea or a guess why wasn't this the definition that appeared?
Well, okay. So to formulate this definition, you need to be in the context of infinity categories. Okay, so that was already a first obstruction. And then it took a while, I think, for people to digest the power of the infinity category machinery in order to realize. It'd be interesting to ask Thomas and Peter how they got the idea of thinking that this was all you really needed for cyclotomic spectra.